Hello everyone, I'm HighSchoolPhysicist. Welcome back to my channel. My motivation in creating this channel is to talk about some topics in physics for audience at high school level or above. Physicists try to find the easiest way to solve problems. This is shown in this video, and this may be appreciated and learned by young students and finally can attract young generations to love physics. Today I'm going to be talking a topic called bound state planetary motion. The agenda for today are introduction, and then Sun-Earth system in circular motion, Sun-Earth system in elliptical motion, Sun-Earth with Lagrangian, this is an advanced topic, and conclusion. To follow this video, you need to use the concepts of gravitational force, centripetal force, kinetic energy, and gravitational potential energy. But don't worry, I will write down all the formulas for these two forces and energies. Secondly, apologize me that calculus differential is used to follow this video in the Lagrangian part. But the good news is this part can be skipped if the viewers feel it is too hard. Introduction. There are two things we learn in physics. The first is bound state, and the second is scattering or collision or decay. The examples for bound state are planetary motions, electron nucleus in atom, for example, is hydrogen atom, and the third is protons, neutrons in nucleus, for example, in helium nucleus. While the examples for scattering, collision, or decay are the billiard balls collisions, electron-electron scattering, or the decay of neutron to become proton plus electron plus antineutrino. So in this video, we discuss bound state, the planetary motion. So relax and enjoy. The simplest model to describe Sun-Earth system is circular motion model. In this model, Earth orbits the Sun in a perfect circle orbit. Here I present 5 parameters, which are ms, or the mass of the Sun, me, or the mass of the Earth, r is the distance between Earth and Sun, t is 1 year, and g is gravitational constant. Here I work gravitational constant with the unit of cubic kilometer instead of cubic meter. Using these 5 parameters, can we calculate the average speed of the Earth, or VE? I present 2 methods to calculate VE. Please pause the video now and try to find the solution by yourself first. Okay, welcome back. In the first method, I used mathematics. Of course, it's just the Earth orbital circumference divided by 1 year period, and the answer is 27.79 kilometers per second. In the second method, I used physics, especially forces. In this two-body problem between Sun and Earth, there are 2 competing forces. Those are centripetal force and gravitational force. These 2 forces must be the same to create a stable bound state. Here we see the formula for centripetal force is me VE squared divided by r. And then for the gravitational force is g me ms divided by r squared. Using algebra, we find that Fe is 29.80 kilometers per second, we see that the two methods give similar VE results. To a more accurate and realistic prediction, we have to use the fact that Earth orbit to the Sun is in ellipse shape. This is the first Kepler's law. So I introduce two more parameters. Those are perihelion distance, or the short distance between Earth and Sun, and aphelion distance, or the farthest distance between Earth and Sun. Using these two extra parameters, we can calculate Earth's speed more accurately. The first method that I used was mathematics. I have to convert from RP and RA into A and B, which is shown on the screen. With these new parameters A and B, we can calculate the average VE by dividing the circumference of the ellipse by 1 year period. I set average because the Earth's speed is not going the same everywhere in its orbit because of varying distances to the Sun. How to solve the problem? Let's go to the next slide. We'd like to calculate the Earth's speeds at two different distances from the Sun, which is Vp for perihelion distance and Va is the speed at aphelion distance. In this case, we have to use centripetal and gravitational forces to solve this problem. And after some algebra and calculation, we see that Vp is greater than Va. The closer the Earth distance from the Sun, the faster it orbits. And this is the second Kepler's law. The third method is Lagrangian method. This is an advanced method that requires calculus, so you may skip this part if you feel it is too difficult. Lagrangian method has a lot of advantages, and it is an effective method to solve the problems analytically. There are 3 steps to solve Sun-Earth problem with Lagrangian. The first is to write the Lagrangian L. The second step is to apply Euler-Lagrange equation to the L. And the third is to solve the equation of motion obtained in step 2. Step 1 is to write the Lagrangian L. What is Lagrangian L? Lagrangian is the difference between kinetic energy and potential energy, or L equals T minus U. As I promised, I write down explicitly T and U for you. T is the kinetic energy, which is half times mass Earth times Vx squared plus Vy squared. Vx is the component of velocity in x direction, and Vy is the y component of velocity. And for U is the potential gravitational energy, is negative G times Earth mass, Sun mass divided by R. Using Pythagoras theorem, R is just square root of x squared plus y squared. Hence, the Lagrangian is shown on the screen. Step 2. Apply Euler-Lagrange equation to dl. Euler-Lagrange equations with two variables x and y are: the first equation is d over dt of the partial derivative of Lagrangian with respect to Vx equal to the partial derivative of Lagrangians with respect to x, and so is for y. I wrote down the result from the last slide for the Lagrangian, and we start calculating this. The first is the partial derivative of Lagrangian with respect to Vx is me times Vx. And then d over dt of me Vx is the same as m dvx over dt, or m times d2x over dt squared. And then for partial derivative of Lagrangian with respect to x is negative g me msx over the square root of x squared plus y squared to the power of 3. And this left hand side must be the same as right hand side as shown in the screen. Step 3 is solve the equation of motion obtained in step 2. The equation of motion that obtained from step 2 are d2x over dt squared and d2y over dt squared. Now we need initial condition for xt, yt, vxt and vyt at t equals 0 second. So let us take the P point as shown in the illustration. Seeing this illustration, we can see that x at t equals 0 equals to xp and equal to negative 147.1 million kilometers. Y0 is 0 and Vx0 is also 0 kilometer per second. But how about Vy at t equals 0, which is the same as Vyp? We will calculate this in the next slide. Now we are equipped with d2x over dt squared, d2y over dt squared, x0, y0, and Vx at t equals 0. Using computational technique, I found that Vy to be around negative 30.25 kilometers per second. For us to reproduce the observation, which are the perihelion of 147.1 million kilometers and the aphelion of 152.1 million kilometers. In conclusion, we have learned about bound state of planetary motion. We have calculated the Earth speed in the simplest Sun-Earth circular motion. We have calculated the average speed using the next more accurate and realistic model, which is elliptical orbit. We have estimated Earth speed using analytical method, that is Lagrangian method. And lastly and surprisingly, Earth mass doesn't have any role in these calculations. This accounts for the equivalent principle, and equivalent principle is the key principle in the most accurate theory of gravitation that we know today, that is general relativity. Again, I want to thank my fellow dark calligraph. Consider subscribing to his channel. See you next time and thanks for watching.